In episode 47, titled Availability Requirements, Turning Uptime Promises into Architecture, the job is to take a statement like, "We need 5 nines," and translate it into concrete design requirements that engineers can actually build and operate. Uptime promises are often made in meetings as if they are simple commitments, but architecture is where those commitments become trade-offs around cost, complexity, and operational discipline. The exam tests whether you can move from vague goals to specific targets and then to design patterns that match those targets. That requires you to think in probabilities, downtime budgets, recovery expectations, and failure scope rather than in slogans. When you can do that translation reliably, availability questions stop feeling like memorization and start feeling like structured reasoning. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Availability is best understood as the probability that a service works when it is needed, not as a guarantee that it never fails. A service can be healthy most of the time and still be unavailable at critical moments, which is why availability is framed as probability rather than certainty. In technical terms, availability is measured over a period of time and reflects how often the service can successfully deliver its intended function. This definition matters for the exam because it pushes you away from simplistic thinking like add redundancy and you are done. Availability depends on more than redundant hardware, including operational processes, monitoring, and the nature of failures you are designing to tolerate. It also forces you to consider that works when needed includes dependencies such as identity services, domain name system resolution, network connectivity, and storage availability. A high availability system is one where the entire service chain is likely to work when the user needs it, not just where one component has a backup. A practical way to capture availability requirements is to define acceptable downtime windows and connect them to business impact. Acceptable downtime is the amount of time a service can be unavailable without causing unacceptable harm, and it should be expressed as a clear window rather than as an abstract percentage alone. Business impact gives that window meaning by tying downtime to revenue loss, safety risks, customer trust, regulatory exposure, or operational disruption. This step matters because two services with the same uptime percentage can have very different risk profiles depending on when downtime occurs and who is affected. For example, downtime during a nightly batch window may be tolerable, while downtime during peak transaction hours may be catastrophic. The exam expects you to ask what the business can actually tolerate, not just what sounds impressive on paper. When you can articulate downtime as a budget and relate it to impact, you have the foundation for real architecture decisions. Defining recovery targets is the bridge between availability promises and recovery behavior, and the exam frequently anchors questions here. Recovery time objective is the time target for restoring service after a disruption, and recovery point objective is the data loss target measured as how far back in time you can lose data and still remain acceptable. These targets force clarity because they separate services down from services down and data is missing, which are different problems with different solutions. Recovery time objective drives design choices like automated failover, hot standby, and multi-zone architectures, while recovery point objective drives choices like synchronous replication, asynchronous replication, and transaction durability controls. When you define both time and data loss targets, you create measurable goals that can be tested rather than promises that can be argued about later. The exam often uses these terms explicitly, and correct answers typically align architecture choices with the stated time and data loss requirements. If you see only one target considered, that is often a sign of an incomplete design. Failure domains are the map of what can break together, and understanding them is central to turning requirements into architecture. A component failure domain might be a single server, instance, or storage volume where failure is localized to one resource. A zone failure domain might include a data center level outage within a region affecting power, cooling, or network aggregation for that zone. A region failure domain expands the scope to a broader geographic area, which can be impacted by major provider events, natural disasters, or region-wide control plane issues. Provider failure domain is the largest, encompassing systemic failures or business-level disruptions that affect a cloud provider's ability to deliver service. The exam tests whether you can match your redundancy approach to the failure domains you claim to tolerate. If your requirement implies surviving a zone failure, single-zone redundancy does not satisfy it, even if it is highly redundant within that zone. Availability architecture is essentially the act of choosing which failure domains you will design for and documenting the ones you are explicitly not covering. Redundancy is often described as a single concept, but in architecture it shows up in different types that address different causes of failure. Device redundancy covers failures of compute nodes, storage devices, or network appliances by ensuring there is more than one capable unit. Link redundancy addresses failures in connectivity paths, such as multiple network links, diverse carriers, or redundant interconnects between segments. Power redundancy addresses failures of power delivery through multiple feeds, backup generators, and uninterruptible power supplies, whether provided by the cloud provider or in on-premises environments. Path redundancy addresses the broader concept of having multiple end-to-end routes for traffic, so that a failure in one path does not isolate the service. The exam often expects you to recognize that redundant devices are not enough if they share the same link, power source, or path, because shared dependencies create shared failure domains. In hybrid systems, these redundancy types become more complex because cloud and on-premises components may have different redundancy characteristics and different operational controls. The right architecture matches redundancy types to the most likely and most damaging failure causes for that service. Graceful degradation and capacity planning are the parts of availability that separate systems that fail loudly from systems that fail usefully. Graceful degradation means that when part of the system fails, the service continues in a reduced capability mode rather than collapsing entirely. This can be achieved through feature toggles, reduced workload modes, queue-based buffering, or serving cached or static responses when dynamic systems are unavailable. Capacity planning during failures is the recognition that redundancy only helps if the remaining components can handle the load when one component, zone, or segment is gone. If a multi-zone service runs at near capacity in normal operation, losing one zone may overload the remaining zone and cause a cascading failure that looks like a full outage. The exam sometimes tests this indirectly through scenarios where failover occurs but performance becomes unacceptable, which is still a form of availability failure. Designing for graceful degradation and failover capacity requires knowing what can be shed, what must remain, and how quickly the system can scale under stress. Availability is not just about being up, but about being acceptably functional during and after failures. A common scenario is deciding whether a requirement maps to a single-zone design or a multi-zone design, and the correct answer depends on the downtime budget and failure domains. If the requirement tolerates short interruptions and does not require surviving a zone outage, a single zone architecture with strong component-level redundancy may be appropriate. If the requirement expects the service to remain available through a zone-level disruption, multi-zone becomes the baseline pattern because it spreads workloads across independent facilities within a region. Multi-zone designs also usually require load balancing, replication, and health-based traffic steering so that user requests shift away from a failing zone automatically. The exam often phrases this as a requirement for higher availability without specifying the design, and your job is to infer which failure domain must be tolerated based on the stated uptime promise and recovery targets. When a question includes tight recovery time objective and low tolerance for downtime, multi-zone is commonly implied because manual recovery rarely meets tight time targets. The right reasoning is to match architecture scope to failure domain scope, then verify capacity and operational readiness. A classic pitfall is confusing backup with high availability, which is one of the most tested misunderstandings in availability questions. Backups protect data by enabling restoration after loss, but they do not inherently keep a service running during a failure event. High availability focuses on keeping the service accessible with minimal interruption, usually through redundant active components and automated failover mechanisms. A system can have excellent backups and still have long outages if restoration is slow, dependencies are complex, or recovery steps are manual. Backups are essential for resilience, compliance, and recovery from corruption or ransomware, but they do not meet availability targets by themselves. The exam often includes an answer option that suggests add backups as the solution to an availability requirement, and that option is usually wrong unless the question is specifically about data recovery rather than uptime. Recognizing the difference helps you choose designs that keep the service up, not just designs that can eventually restore it. Another pitfall is ignoring maintenance windows and update risks, which can cause outages even in systems that are architecturally redundant. Maintenance is a fact of life, whether it is patching, upgrading dependencies, rotating certificates, or changing configurations. If you do not plan for how maintenance impacts availability, you can accidentally schedule downtime that violates your uptime promise, or introduce changes that trigger cascading failures. Update risks are also significant because many outages are self-inflicted through misconfigurations, incompatible versions, or poorly tested rollout procedures. Multi-zone and redundant designs can still go down if the same bad change is applied everywhere at once. The exam tests this by describing planned updates that cause outages and by expecting you to incorporate safe deployment patterns and maintenance planning into availability thinking. If the service has strict availability requirements, maintenance must be designed to be non-disruptive through rolling updates, blue-green deployments, or controlled canary releases. Availability architecture includes operational change control, not just hardware and topology. Quick wins often come from tightening the operational loop, starting with monitoring, runbooks, and failover tests that turn assumptions into verified behavior. Monitoring provides early detection of failures and performance degradation, which reduces downtime by accelerating response and enabling automated remediation. Runbooks provide documented, repeatable steps for handling known failure scenarios, reducing confusion and time loss during incidents. Failover tests validate that redundancy and recovery mechanisms actually work under real conditions, because untested failover is frequently broken failover. These quick wins matter because availability failures are often about response time and execution under stress, not just about topology. The exam frequently rewards answers that include testing and documentation because they show an understanding that availability is operational as well as architectural. If your design is theoretically resilient but never tested, it is not truly meeting the requirement. These practices also help you refine recovery time objective expectations realistically based on observed recovery behavior. A useful memory anchor is target, domain, redundancy, test, document, because it captures the workflow that turns an uptime promise into an implementable plan. Target refers to defining the availability objective and recovery targets in time and data loss terms. Domain refers to identifying the failure domains you must tolerate, from component through zone, region, and provider. Redundancy refers to selecting the right redundancy types, including device, link, power, and path, and ensuring capacity can carry the load during failures. Test refers to validating failover, recovery procedures, and degradation behavior through controlled exercises. Document refers to capturing requirements, assumptions, and runbooks so the design is operable and repeatable. This anchor is helpful on the exam because it keeps you from jumping straight to technology choices before clarifying what the requirement truly demands. When you can walk through the anchor in order, you can justify your architecture decisions clearly. To apply the concept under exam conditions, imagine being given a stated recovery time objective and asked to choose an architecture that meets it. If the recovery time objective is tight, relying on manual restoration from backups will usually not meet the time target, pushing you toward automated failover and redundant active components. If the recovery time objective requires continued operation through a zone failure, multi-zone design becomes necessary, paired with health checks and load balancing that can shift traffic quickly. If the recovery time objective is more relaxed and downtime is acceptable during certain windows, simpler designs may be sufficient, but they still need clear monitoring and recovery procedures. The point is that recovery time objective is not just a number. It is a forcing function that constrains which recovery mechanisms are viable. The exam expects you to recognize these constraints and choose patterns that can realistically meet the target. When you align recovery time objective with automation level and failure domain tolerance, your answers become consistent. To close episode 47, titled Availability Requirements, Turning Uptime Promises into Architecture, the essential steps are to translate promises into targets, map those targets to failure domains, and then build redundancy and operational discipline that actually meet the targets in practice. Availability is the probability a service works when needed, and improving it requires clear downtime budgets, business impact understanding, and explicit recovery objectives for time and data loss. Failure domains from component to zone to region to provider determine how much redundancy and distribution you need, and redundancy must include not just devices but links, power, and paths. Graceful degradation and capacity planning keep services usable when parts fail, while monitoring, runbooks, and failover testing turn design assumptions into proven behavior. The pitfalls of treating backups as high availability and ignoring maintenance windows are common sources of outages and common exam traps. Your rehearsal assignment is to rewrite one vague uptime promise into a concrete requirement statement that includes acceptable downtime, recovery time objective, recovery point objective, and the failure domains you will tolerate, because that rewrite is how you convert talk into architecture. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.